Okay, in this lesson, we're again looking at systems of equations and at solving them. And this one, we're going to start with this question. Since a solution can be thought of as the intersection of two lines, how many possible solutions are there? Okay, if we think about that, in the first case, if we've got two lines, really they can only intersect at one point. So there's one solution. However, if we have two lines that run parallel to each other, you can see that they never intersect. There's no point that will make both of those equations true. So we can also have situations where there is no solution. And this is called an inconsistent system. And the third example is, what if the lines are collinear? That means that we have two equations, but when we graph them, they both line up one right on top of the other. In that case, there's an infinite number of solutions because every point on one of the lines is also on the other. So an infinite number of solutions. And that's called a dependent system. Now, the equations that, or the systems that we looked at as a result of that first lesson, all of those were of this first type that had one solution. So I want to do a couple of examples with you so that you recognize when you have an inconsistent system or a dependent system. So with this example, the first one we're going to look at, our first example is 4x plus 6y equals 12. And 6x plus 9y equals 12. So there are my two equations. If I look at those, if I look at the 6 and the 9 for the y's, I can turn those both into 18 quite simply so that I can use elimination and eliminate the y's from the system. So for this first equation, I'll multiply it by 3. So I'll have 12x plus 18y equals 36. And the second equation I'll multiply by negative 2, and I'll have then negative 12x minus 18y, so that these are now equal and opposite and will be eliminated, equals negative 24. So now when I add the two equations together, my y's disappear because 18y plus negative 18y gives me 0. But look what happens to my x's. They also have disappeared. I've got a 12x minus 12x is 0. So I end up with 0 equals, if I add these two together, I have 12. So this is a statement that's not true. 0 does not equal 12. And the x's and y's have both disappeared. So x and y are both eliminated in the same step, and we end up with a statement that's not true. So our solution is the null set, or there is no solution. This is one of those systems that's an inconsistent system. The two lines, if we were to graph those two lines, they would be parallel to each other. So they would have the same slope, but a different y-intercept. So now let's look at another example. I've got one here where my first equation is y equals 3x minus 2, and my second equation is 15x minus 5y equals 10. Since the first equation already has one of the variables isolated, the y, I'm going to use substitution, and I'm going to substitute 1 into 2. And what we're looking at today works or is true whether we use substitution method or the elimination method. So if I substitute 1 into 2, I know what y is here, so I'll have 15x minus 5 times 3x minus 2 equals 10. So 15x minus, and if I multiply through there, I get 15x plus 10 equals 10. Well, I've got 15x minus 15x, so at the same stage where I've eliminated y, I've also eliminated x, and I have 10 equals 10. Now that's a statement that's true. So this is one of the examples of where we have a dependent system. These two lines, if I was to rearrange the second equation into y equals mx plus b format, it would be exactly the same as the first line, okay? So the lines coincide, the system is dependent. Okay, so really there's an infinite number of solutions, and if we had to write our solution set out, we could say that the solution is the set of all x and y pairs such that y equals 3x minus 2. Okay, so every point from that first line is a solution to the whole system, or every point on the second line is a solution. And you would only need to write down one of these, such that 15x minus 5y equals 10. If the x and y pair satisfies this situation of 15x minus 5y equals 10, then that x or y pair is a solution to that system. One example that our book uses for solving linear systems is called a break-even analysis, and it's just neat to see that example. So this is a good application for linear systems. So I want to introduce a couple of functions to you. The first one is called the revenue function. And so we're thinking in terms of business, and we're thinking also in fairly simplistic terms, okay? So we're not taking care of all of the factors that lead a business to the break-even point, but we're looking at a couple of them and looking at it as a possible example for systems of equations. So the revenue function we usually write as r of x, or r at x, equals, and it'll be the price per unit. So the revenue function is the money that comes in. So it's the price per unit times x. So x really represents the number of units. And it's the price per unit sold. Sorry, that should have been in there earlier. So you take the number of units sold, multiply by multiply by their price, and that gives you your revenue function. Your cost function, and we'll call that C at x, is equal to your fixed costs plus the cost per unit. So that will be the cost to manufacture your unit. And again, you're going to multiply that by x, the number of units that you produce. Okay, so your revenue function is going to look something like this. If you sell, this is your units, okay, and there's your revenue here, and it's in dollars. So if you sell 0 units, your revenue is also 0. So your revenue function is going to look something like this. Your cost function is going to look something like this, where you have fixed costs. So for instance, if you're looking at the cost function for a year or a month or for a given period of time, that would be the cost of the building, the cost of your power, the cost of your staff, things that don't change based on the number of units. And then you're adding that the cost to produce each item. So your cost function might look something like that. So your break-even point then is the intersection of those two functions. So there's my revenue function, there's my cost function, and at some point where they intersect, that's where you break even. At this point, at any value less than this point, you can see that the costs are higher than the revenue. So you're losing money here. And anything to the right of that point, you can see that the revenues are greater than the costs. So actually here, you're in the profit zone. Okay, and the break-even point is the intersection point of those two functions. So let's look at an example. So here's our example. The fixed cost for producing hockey sticks at a local plant is $100,000, and it will cost $8 per stick to produce them. The finished sticks will sell for $33. So the first part of this question will be to write the cost function. The second part will be to write the revenue function and then to determine the break-even point. Okay, so the cost function could be represented as C at X equals, and remember it's the fixed cost plus the cost to produce each unit times the number of units. And X represents the number of units, so it'll be 100,000 plus 8X. Okay, our revenue function R at X is how much money are we taking in for the number of sold, so it'll be 33X. So our break-even point will be where those two intersect. So it'll be where C at X, where the cost is equal to the revenue, whatever that X value is that makes that true. So let's set these two equal to each other. So now I'm looking at these two functions, and this is a whole new way of solving a function, a system, because we're not quite doing substitution and we're not quite doing elimination. But what we're doing is comparing the two functions, and when we set them equal to each other, we find the break-even point or the crossing point of the two lines if we were to graph them. So I've got 100,000 plus 8X equals 33X. Let's subtract 8X from both sides of this equation. So I've got 100,000 is equal to 25X. So if I divide both sides by 25, I'll have X equals 4,000. Okay, so let's take a look at what the revenue and the function and the cost function are for that. The revenue at 4,000 is going to be 4,000 times 33, which is 132,000. And let's take a look at what the cost function for that is as well. So the cost at 4,000 is 100,000 plus 8 times 4,000, which again will give us $132,000. Okay, so the fixed costs and the revenue, sorry, the total cost function and the revenue function are both equal when we make and sell 4,000 hockey sticks. So if we think about what this means, if they produce and sell fewer than 4,000 hockey sticks, they're in a net loss situation. And if more than 4,000 sticks are produced and sold, they're in a profit situation. So that's a good example of looking at linear systems and looking at systems of equations and comparing the two to find where they intersect, or what in this case the break even point for that system is.